Hello friends and welcome to Geeks for Geeks. In this video, we will be learning an efficient way of Huffman coding when the data given to us is sorted. So let's have a basic idea about Huffman coding. We have covered all this and a lot about Huffman coding in our previous video. So it is strongly advised that you check out that video before. So this is a lossless data compression algorithm where each character is assigned a variable length code. This variable length code depends on the frequency of input character. That is, more the frequency, shorter will be the code. All the code that are assigned to the character are prefix code, which requires that there is no whole code word in the system that is a prefix of any other code word in that system. This property makes sure that our data is uniquely decodable. This is the data information. Our data consists of 6 characters and these are their frequencies. Also note how the input is sorted in non-decreasing order of frequency. Now in the previous video on Huffman coding, we have covered a greedy approach n log n algorithm. Here, however, we can use one thing to our advantage. That is, the data given to us is sorted. So here we devise an efficient approach and these are the steps that will improve the running time complexity. These steps do look scary, however are very simple once you go through the complete video. We'll dry run these on our data that was previously shown. So let's get started. This is the data and the first step says to create two empty queues. Here they are, Q1 and Q2 both initially empty. Second step says to enqueue each unique character in non-decreasing order of frequency. We enqueue A, then B, C, D, E and finally F. The second queue is still empty. Now since all the data is in our queue, let's get rid of this table and have some free space. In the next step, we are required to dequeue two nodes having minimum frequency. For this, we have to check the front of both the queues in order to find the minimum. Since second queue is empty, we take two minimum node out of this one. Node A with frequency 5 and node B with frequency 9 are the required nodes. In the fourth step, we have to form a new internal node and add the node with lesser frequency to its left and with greater frequency to its right. Also, the frequency of this new node is the sum of frequency of its two children. After this, we have to enqueue this new node to our second queue, Q2. Finally, we have to repeat step 3 and 4 until only a single node remains. So, third step was to dequeue two nodes with minimum frequency. We look at both the queues. Here, C has lesser frequency than N1, so we dequeue it. Again, D has lesser frequency than N1, so we dequeue it. Now the fourth step was to form a new internal node. We form new node N2, add lesser frequency node C to its left and greater frequency node D to its right. Assign its frequency as the sum of frequency of C and D. And finally, enqueue it to Q2. Since we have more than one node, we again repeat step 3 and 4. Here N1 has lesser frequency than E, so we dequeue it. E has lesser frequency than N2, so we dequeue it. Now we form new node N3, assign N1 to its left and E to its right, and its sum as the sum of its two children. We finally put this new node to our second queue. We still have more than one node left. So again, we repeat step 3 and 4. Node N2 has lesser frequency than F, so we dequeue it. Out of these two, N3 has lesser frequency, so we dequeue it. We form new node N4, assign N2 to its left and N3 to its right, and its sum as the sum of its two children, N2 and N3. We finally put this node N4 to our second queue. We still have two nodes left. We dequeue both the nodes. Form a new node N5 with F to its left and node N4 to its right. Enqueue this back to second queue, Q2. Now we have only a single node left, and so we can stop this algorithm. This remaining node is the root node of our Huffman tree. Let's have a look at our Huffman tree. Node N5 is the root node with F to its left and node N4 to its right. Let's expand all the internal nodes. N4 has N2 at left and N3 at right. N3 has N1 on left and node E at right. Next, node N2 has C and D on left and right. Finally, let's see for this N1 node. N1 has A on left and node B on right. So, this is how our Huffman tree would look like. Now to generate code from this tree, we have to assign 0 to each left edge and 1 to each right edge as we cover all the root to leaf path. See 0, 1, then 0 and 1 and so on. These are the codes formed for each character. Let's see how we obtained for node C. So here is C. We start from root, go to right, go to left, again left. So we have 1, 0 and 0. Let's generate for A. Here we have A. We start from root, go to right, again right, to left, to left. We have this 1, 1, then 0 and 0. Similarly, we do for all the characters. Let's now see the implementation of this algorithm. Here we have a code which is same as given on GeeksforGeeks. Here we have a function which perform all the 5 steps that we have discussed earlier. It inputs all the unique characters in our data, their respective frequencies, and the count of such character. It then creates 2 empty queues and enqueue all the data in the first queue. Then we iterate until the first queue is empty and the second queue contains only a single node. Each time we dequeue 2 nodes by examining the front of both the queues and assign one with lesser frequency to variable left and with higher frequency to variable right. We now form a new internal node and assign its frequency as sum of frequencies of its two children, and also add left to its left child and right to its right child. Finally, we enqueue this node to our second queue. Once this loop is over, we return the only node that is left. This is the findMin function which gives minimum frequency node by comparing the front of two queues. So if first queue is empty, it dequeue the second one. If second queue is empty, it dequeue the first queue. Okay, so these comments are wrong. Finally, if both the queues are non-empty, we compare the front of both and return the one having minimum frequency. This function will help us to generate codes using a Huffman tree. We input a pointer to root node, an auxiliary array to store the code formed so far, and the size of it. We assign 0 if left edge exists and recur. Similarly, if right edge exists, we assign 1 and recur. If we reach a leaf node, we print the code value stored in our array. Now let's see the complexity of this code. The code will run in big O of n time. This is only because of the fact that the data given to us was sorted. Here n are the number of unique characters. So with this, we come to an end of this tutorial. If you have any doubts or suggestions, please leave them in the comment section below. Thanks for watching.